guys, this is Dr. Al Jafri from ELG5195, and in this video, we're going to cover something called the FPGA, which is the Field Programmable Gate Arrays, in a different way. So, traditionally, I give you the lectures in a theoretical part. However, in this lecture, I would like you to do a small project using the Quartus or the Intel Quartus software. So, before I get started, let me go and remind those who did not evaluate the course. Please go ahead and evaluate the course by visiting this link. Okay, so you can go to evaluation URL and you can evaluate your course. And I really appreciate a constructive feedback from you guys. Okay, now, so what is the FPGA? So FPGA is belonging to the family of programmable logic blocks. So the FPGA, or the Field Programmable Gate Array, are semiconductor devices that are based around a matrix. There will be a matrix of what? A matrix of configurable logic blocks, CLBs, connected via programming interconnects. So what does that mean? That you can implement multiple combinational and sequential circuits, and eventually you can implement a simple computers using the FPGA, and you can upload your design there, verify it, then send it for fabrication. So the FPGAs are reprogrammed to desired application or functionality requirements after manufacturing. Okay, so one of the pioneer software to interact with the FPGA is called the Intel Quartus software. So the Intel Quartus software is in the number one in performance and productivity for the complex programmable logic devices, the CPLDs, as well as for even the ASIC. And those who are from the networking background, they know what's the ASIC. So for the Cisco routers, switches, and even the firewall, they're an ASIC-based appliances. ASIC means application specific integrated circuit. So those who are reading the system on the chip or doing some reports for the system on the chip, they're familiar. What do I mean by ASIC? So instead of having a general computer that can do multiple things, we will have a specific device. That specific is optimized for a specified application, such as preventing malicious attack or doing the routing. Okay, so when it comes to the FPGA, the University of Ottawa has the Cyclin FPGA here, and it's found at the CBY lab at the 3rd floor. And in this video, I'm gonna ask you to implement a multiplier or a parallel multiplier using the one-hot assignment method. You remember the one-hot? The one-hot employs one flip-flop for each state. Exactly, one flip-flop for each state. Okay, so what is the parallel multiplier? Something similar to what I covered in the parallel adder or parallel additions. The parallel multiplication is nothing more than adding and shifting at the same time. What does that mean? So similar to the subtractor, using the adder itself, we can implement a parallel bit multipliers. Okay, so in this project, I would like you to implement a parallel multiplier, and that's capable for multiplication of two positive. So don't pay attention to the sign bit. Two positive 4-bit numbers. Okay, so basically we're gonna require the a 4-bit multiplier register and a 4-bit multiplicand register, and an 8-bit registers for the product itself. So let's take a look at this example. You see, here what I'm doing is I'm just doing the addition, and then I'm shifting, addition and shifting. And as we can see, eventually when we are multiplying two 4-bit numbers, we're gonna end up with having a number with 8-bit long. Okay, so that's why I need an 8-bit register. Okay, so the product register here in this design, okay, serve as an accumulator. What does it mean, accumulator? It's to accumulate the sum of what? To keep accumulating the sum of the partial product. As you can see, we're adding, we're shifting, then adding, we're shifting, we're adding. Okay, so instead of shifting the multiplicand left each time before adding it, it's more convenient to shift the product register to the right each time. Okay, so in this figure, as we can see, we will see a block of the desired diagram for the parallel adder, and as indicated by the arrows, you see, as indicated by the arrows, like look to the arrows where we're shifting. Okay, the 4 bits from the what? 4 bit from the accumulator and 4 bit from the multiplicants are connected to the adder's input. Okay, the 4 sum bit and the carry output from the adder are connected back where you see that we're connected back to the what? To the accumulator, because as we can as I mentioned, so instead of shifting the multiplicand left each time before adding it, what I'm doing is it's like, you know, I'm shifting the product register to the right each time. Okay, so how this can be achieved is using what? Using a control unit. So that control unit, when adding, or like when an addition pulse PA occurs, the adder outputs are transferred to the accumulator, which in turns causing the multiplicants to be added to the accumulator. An extra bit at the left end of the product register temporarily stores any carry which is generated from the multiplicand, okay, and then added to the accumulator. Okay, as we can see, like in order to what? In order to perform this, what we have to do is, okay, when you read this, like a problem statement, since the 4 bit of the products are initially unused, we will store the multiplier in the in this location instead of in a separate register. As such, the multiplier bit is used. It is shifted out the right end of the registers to make room for the additional product bits. The pulse PS causes the content of the product registers, including the multiplier, to be shifted right one place. The control unit puts out the proper sequence of add and shift pulses after a start signal N1 have been received. If the current multiplier bit okay, is 1, the multiplicand here is added to the accumulator following by a right shift. If the multiplier bit is 0, which is basically, you know, doing the addition will not do anything, so the addition is skipped and only the right shift occurs. So given this problem statement and given the design given to you here, okay, I would like you to design the control unit of the multiplier by using the one-hot approach and D flip-flops. So to make it easy, I'm gonna give it to you using the D flip-flop. So like as an assumption, you can assume that the 2 operands are loaded in the 2 registers at the beginning of the multiplication cycle. So what you need to do, you need to provide the finite state diagram of the control unit along with its state table, okay? And you need to provide the logic equation of the next state and the output function. And finally, the logic diagram of the circuit that implements the control path, okay? And after designing the control unit, okay, something similar to whatever I've shown you in the like in the parallel adder, what you have to do is you have to create a 1-bit adder, then create a block from that 1-bit adders to create what? A 4-bit adders. And once you have this 4-bit adders, what we have to do is you can create a block of that 4-bit adders. Don't worry, I'm gonna show you how to do this in the next in the upcoming time, okay? And remember to create a file to using a 4-bit D flip-flops to create a 4-bit register and 8-bit 8-bit D flip-flops to create a what? An 8-bit register for the product, okay, to hold the product. So in order to do this, I don't want you to do it, to design it using what? Using the like a pencil and paper method. No, I want you this time to go to, you know, like to the link provided here, studentslab.ualawa.ca, and there follow the whatever I've shown you here. So what you have to do is to install the VMware Horizon, and after installing the VMware Horizon, you will be capable to launch the Quartz, okay, the Intel Quartz software remotely. And then what you need to do is to create a project. Then that project where you need to use the Cyclin EPE processor. And after that, just follow the tutorial that I'm gonna show you shortly, okay? So as you can see here, we can lock for Quartz, and we're gonna launch it. After you launch the Quartz, you can you can create a guys? You can create like, you know, run the software, okay? And then you can create a project, okay, here, okay? So that's it for that's it for this lecture, guy, and I'm gonna leave you with the tutorial from the ITI course, ITI 11 course, to teach you how to interact with the Quartz, okay? Have a nice day. You have, by the way, you have till the next lecture to send me the file for your full design. Remember, in your full design, what I want to see the control unit as well as the full 4-bit parallel multiplier, okay? And please send it to me via what? Via Microsoft Teams, okay? You have till the next lecture to send me that. Have a nice day.